We are now going to consider a type of technique called RungeKutta techniques, and in particular in this video we're going to consider second order RungeKutta techniques. And these two fine gentlemen down here, Runge on the left and Kutta on the right, European mathematicians from the late 19th century. So the RungeKutta methods start with the same basic idea as the Taylor series method. So we write the solution that we would like to find, y of ti plus h, as a Taylor series expanded about the point ti, or the time ti I should say. So that's just the Taylor series written out again. What we want to do this time, however, unlike in the Taylor series method, is to estimate these higher order derivative terms without using the original ODE. So we don't want to know what that right hand side is. We somehow want to do this differently. Of course, the more terms we estimate, the higher the accuracy of the method. Now, because dy dt is equal to f, we know that y double dashed is equal to dy dashed dt, which is equal to d by dt of f of t and y, and using the chain rule, that is simply df dt plus df dy times dy dt. And because we know that dy dt is equal to f, we can simply write that the second derivative is equal to df dt plus f times dy. So let's substitute this expression into our Taylor series. So that we're going to get rid of this second derivative term here. This gives us then that y of ti plus h is equal to y of ti plus h times the function plus h squared on 2 times df dt plus f df dy. This is just this term here substituted in for y double dashed. Now, of course, we know what f of ti yi is because we know what the function is, we know what the time is, and we know what our current solution is, yi. However, we don't know what these things are, and we need to find some way of estimating them. That term and that term there. And what we're going to do is we're going to look at a couple of different ways of using what's known as RungeKutta theory to estimate them. So the basic idea behind RungeKutta theory says that the correct average of the slope, or correct value of the slope, and by correct here I mean the value of the slope that if you started at the beginning of the interval and you took one step to the end of the interval would give you exactly the correct answer. RungeKutta theory assumes that over this correct value over one step can be written as a linear combination of values at certain points inside the step, and these points are denoted with tk and yk. So these lie within the step. They could include the endpoints, but they don't have to. So graphically what we've got is we have a solution there, that's the blue curve. We're starting at ti, and we want to get the solution at ti plus h. And we're going to use something that we need to calculate at some point in this interval. Let's call it ti plus alpha. Okay, so we want to have a slope, for example, at the beginning, plus some slope at this point t is equal to ti plus alpha, and we want to average them in some kind of a way so that if we start here, we'll end up at the correct solution at the end point. Now, the particular combination of these two slopes is also something that we need to determine. It's not necessarily just an average. It can be different to a straight linear average. It'll be a weighted average of some sort. But the problem here is determining which points we need to use and exactly what kind of linear combination do we need. Are they going to be equal weights, unequal weights, and how do we determine that? So let's just go back and take our Taylor series expression again, where we have removed the second derivative term. I've just rewritten it there. And what we're going to do is we're going to take an h out of all of these terms. So we've just taken an h out the front, and we've got written f is in here, and these two terms at the top here then just become h on 2 times df dt plus h on 2 f times df dy. So we've just slightly reordered this expression here. I've rewritten that again at the top. So what this means is that this term in braces here, if we can calculate it exactly, is our better estimate of the slope, because if we can use this, we can see that the error is going to scale like h cubed. So that's what we're trying to find, that thing in the brackets there. It's the red line in the figure below. It's the red line that has the slope that if we start here and we follow that slope, we'll end up at the point where we want to be. It may not be obvious, but this term in brackets bears a striking resemblance to a two-dimensional Taylor series. So let's just write two-dimensional Taylor series using alpha and beta. So we know that the function of t plus alpha and y plus beta is equal to f of t and y plus alpha times df dt plus beta times df dy, plus some higher order error terms that scale like alpha squared and beta squared. So we can see, just looking up here, there are some significant similarities. So if we let alpha equal h on 2 and beta equal h on 2 times the function value evaluated at ti and yi, then what we have, we can effectively rewrite this term at the top here as f of ti plus h on 2 plus f evaluated at ti plus h on 2 and yi plus h on 2 times f. So we've reduced this term here to a function of valuation at some other point. In this case, it's given by ti plus h on 2 and yi plus h on 2 times f. It might not be immediately obvious to everybody, but this is exactly the midpoint method, where this here is the predictor step, and this entire thing is the corrector step. Okay, so we have derived the midpoint method using RungeKutta theory. In terms of this theory, the points at which we need to find the slope is only the midpoint. In other words, it's this point here. Because there's only one point, there is no linear combination in this particular case. It's actually only one point. So, are there alternative and perhaps better schemes for doing this? Well, of course there are. So let's go back to this expression that we derived before. This is our Taylor series expansion with a second derivative replaced across there. Let the term in braces be equal now to a linear combination of the starting slope, which we always know, and the slope at some other point. We don't know what this point is, we need to try and find it. We're going to call that point ti plus alpha and yi plus beta. Now this is not going to be an equal combination, it's going to be a combination of that we need to try and estimate. So let's write the term in braces, so that's the same as this term up here, as equal to c1 times the function value at the beginning point plus c2 times the function at some other point in the interval, ti plus alpha, yi plus beta. So I've just rewritten that expression at the top of the page here. We'll leave the left-hand side as it is, and we'll take the right-hand side, and we're going to expand this term into two-dimensional Taylor series. So the left-hand side stays the same. The right-hand side becomes equal to c times f, c1 times f, plus c2 times f plus alpha df dt plus beta df dy plus some error terms. If we now just group these terms together, we see this is equal to c1 plus c2f plus c2 alpha df dt plus c2 beta df dy. So now what we can do is we can start having a look at that expression there and the term up here in braces, because those two things are effectively equal, at least to within some error tolerance. So if we compare those terms, we can see that, first of all, c1 plus c2 has got to be equal to 1. C2 alpha has got to be equal to h on 2, and C2 beta has got to be equal to h on 2 times the function evaluated at the beginning point. So let's just write those three conditions out there, sorry. So once we've found C1, C2, alpha and beta, the ODE update becomes y of ti plus h is equal to y of ti plus h times C1 times the function value at the initial point plus C2 times the function value estimated at this point. And again, this will be a predictor step, and this entire thing will be the corrector step. However, we have three equations and we've got four unknowns, C1, C2, alpha and beta. So there's actually an infinite number of solutions. So for example, if C1 is equal to C2 equal to 1/2, that means that A is equal to H and B is equal to H of F, evaluated at our initial point, Ti, Yi, and this gives us that expression there. Well, that's exactly Hoyne's method, and you should prove this to yourself. That's the Hoyne predictor, and this entire expression is the Hoyne corrector step. So those are the equations we have to satisfy. What happens if we set C1 equal to 0? That gives us C2 is equal to 1, alpha is equal to h on 2, beta is equal to h on 2 times f of ti, yi, and this gives us the midpoint method again. And you can do all kinds of different things with C1 and C2, coming up with different values for alpha and beta.